Good morning, everybody. At least I think it's a good morning. We're going to find out here just real quick. Recording the first of the YouTube channel videos here from the nerve center of the AERO Educator Network, deep in the heart of New Orleans, Louisiana, where we've had snow. I know. Anyway, that's where we are. We're trying everything. Guys, we've got a lot of new stuff this morning. We have a new platform that we're using, which is our new YouTube channel. We have a brand new camera that we're using here this morning, the Canon XF305, which I look fabulous. I'm just saying. So that's what we're doing here today. We're going to go ahead and continue today with instruments and kind of do our wrap up. The one thing I'm not 100% sure of here, kids, is the volume, because I've got something here. It's showing that I'm doing great. I'm looking at a monitor kind of here behind the camera that I'm looking at the volume levels. It says that I'm awesome, but I don't know. We'll find out. So there's that. So guys, where we're going to pick up is I want to talk to you first. Well, yeah, I've had these for my close-up work here. Let's put those somewhere else. And yeah, it was dusty, so I dusted. Yeah, we'll put that over there. Yeah, so here we go, working with this stuff here, making sure that everything is on and we are live. Good morning. How you doing? Okay, there we go. Guys, we're going to start here, and I'm going to switch the view here to the book here. Let's see, where can I, man, trying to, oh, by the way, I'm going to have a sip of coffee. Here we go, pardon me. I'm going to do this off camera. Oh, was that on camera? Okay. So here we go. We're going to look here, guys, here at the color coding on the airspeed indicator again. This is one of the things that I just want to make sure that you guys are clear on, and that has to do with those terms that we call V speeds. So for instance, when we look here at the green arc, remember the green arc here in this, can I get that a little larger? How do I do that? Hang on here, zoom. I don't want to do it that much. That's going to be just a little much there, I think. Yeah, dang it. I'll fix that later. I thought I could zoom in on that, but I can't, can I? Just remember that the green arc, anytime that you see that on an airspeed indicator, what it's talking about there, it's VNO, which is going to be your maximum structural cruising speed. It is the normal operating range with your aircraft in a clean configuration. However, you know, it's just not as easy as just saying, well, VNO is normal operating range. It is the structural cruising speed. So the thing that you're going to have to learn is going to be all of those V speeds. You have a chart down there that shows you those V speeds, and I think I showed that to you one other time. You're going to need to know what those V speeds stand for. So what VS1, VSO, VNO, VNE, also VA. VA, or depending upon which aircraft that you're flying, or something called VO. It's going to be something that we call maneuvering speed. Maneuvering speed is that speed at which, when we start getting bounced around in the airplane, this is where VA comes in. So in the mountains, clearly, we're going to have some turbulence occasionally. When that happens, and it starts to get just a little bit beyond just kind of the mild little burble that you get, you know, when you fly, when you start getting kind of bounced around the cockpit, you're going to need to slow that airplane down. The reason that you want to slow that airplane down is because if you get a real big gust one way or another, it can put excess structural loads on that airplane. And when that happens, bad things can happen. So slowing that airplane down gives you a greater margin of safety with regard to the constructional integrity of your airplane. Oh my God. Structural. Stand by. Structural integrity of your aircraft. Goodness. Slowing the airplane down will allow you to fly in what we call VA. The reason that VA is not indicated on your airspeed indicator is because it is wholly a function of the weight of your aircraft. The heavier you are, the higher your VA indicated airspeed is going to be. Remember, VA is what we call maneuvering speed. VA is maneuvering speed. Cirrus, I think, calls it VO, which is like operational speed. But like Cirrus kind of does their own thing with stuff anyway. So that's kind of how they do it. But VA is maneuvering speed. Maneuvering speed is dependent on the weight of your aircraft. For instance, on the Diamond, and I'm going to forget this here this morning because it's the morning for it. The Diamond VA, if I remember correctly, VA is 108 knots when you're heavy, and then I think it goes down to like 98 or 96 knots when you're lighter. And we'll get into that once we start getting into the operational elements of the airplane and we get into performance. We'll look at that. But it's a lighter range. I think VA on my airplane is 125 and it goes down to like 112 or something like that for my airplane. You'd think I'd know that, wouldn't you? But that's not indicated on the airspeed indicator. VA maneuvering speed, not indicated on the airspeed indicator. And it is a function of the weight of your aircraft. What that allows you to do, according to the FAA, is this. It allows you to make one full deflection of any primary control surface without structural damage to the aircraft. One full deflection of any one primary flight control surface without structural issues to the airplane. That's the speed at which that can happen. All of this changed after November of 2001, I believe it was. And that's when that Airbus flew into the wake turbulence of a departing 747 out of New York. And the co-pilot who was flying at the time was trying to steady the aircraft, and he was sawing the rudders. And by putting that much rudder pressure back and forth on the rudders, it ripped the vertical tailplane off the airplane. And when that happened, the airplane sadly lost control, fell out of the sky, and broke apart over Queens. And it was a really sad kind of a thing. So that's kind of where maneuvering speed comes in. Okay, so know those V speeds. We're going to go down here and look at some of these other things. I'm going to blow through these things that we have already talked about. Indicated airspeed, true airspeed, we've covered that. True airspeed, yes, we've covered this. I'm going to go through this here also. Know what the errors are for your instruments. Okay. Know what errors are caused by and what those are going to look at. Okay. Make sure you know those. The altimeter. Know how it works. Oh look, there's how it works. Okay. Know what the hands mean. Know what they are. The pressure window, and by the way, I misspelled Colesman. I said K-O-H-L. I think I was thinking of Kohl's as in like, the retail store, Kohl's. It's K-O-L-L-S-M-A-N. There's that. Also know that we turn our altimeters to 29.92 when we're at or above 18,000 feet MSL, or what we refer to as flight level 180. The reason that we do that is to put everybody on the same sheet of music. When you're above 18,000 feet. Guys, I'm having a rough morning this morning here speaking. So 18,000 feet or flight level 180. And again, the reason that we do that is because when you get above 18,000 feet, you're not going to hit anything. You know, we're above all the mountains in the lower 48, and we're above all of the towers and all that other stuff, so we're not going to hit anything above there. And the problem is that, you know, remember me telling you that flying in the mountains, if you go more than about 10 minutes without changing your altimeter setting, you know, with getting another reading from another airport, you should start getting a little, you know, twitchy with stuff, because you've got to change that quite a bit. You may go, you know, in Iowa or Kansas or some other place like that, and you may not have to change it as much, but just know that your weather changes, especially your air pressure changes quite a bit in the mountains, primarily because of the orographic nature of the air as it moves over and around our mountains. And so that pressure changes quite a bit, and you need to change it often. If you do that as you're flying over these things at high air speeds, at flight level 180 and above, you're going to basically have a guy just sitting there and just twisting that knob all the time, and that's just not practical. So to put everybody on the same sheet of music, 29er.92, that's it, and we take those little variations that we have as we fly through the air mass, because as long as everybody is on that page, then that altimeter is going to, the aircraft altitudes, everyone is going to stay together. So there you go. There's that. Back here. All right, there's more presentations of this. Check the altitude accuracy on the ground. Normally what should happen is that when like in Aspen, when they give you the altimeter setting in Aspen, you should be within plus or minus 75 feet of the published altitude for that airport with that given altimeter setting. So you need to kind of check that also. Now then, they call these things altimeter errors, but this really is not an altimeter error. Think about this. Remember that what I said about flying at flight level 180 and above, and we kind of take those little given changes, you know, in the air masses there with regard to pressure. Well, that's a little tougher to do when you are closer to terra firma, especially in our part of the world. And so keeping that altimeter setting correct for your specific locale is extremely important. Because if you think about the way that an altimeter works, and you know that with higher pressure, that little squeeze box inside is going to get smaller. With less pressure, it's going to increase. So we have to think about this flying from one air pressure mass to another air pressure mass. And this is where they come up with the expression, high to low, look out below. High to low, look out below. Because what will happen is that in that case, if you do not change your altimeter setting and you fly from an area of high pressure to low pressure, your actual altitude will be lower than your indicated altitude. You will think you're up here, but actually you're down here. And that could be catastrophic, especially in our part of the world. And here's the way that works. Here comes Superpilot flying along here at, let's say, 10,000 feet. He's flying along at 10,000 feet, and he is flying from an area of high pressure to low pressure. So here he is, let's say that he's flying along here, and he's got an altimeter setting of 30.80. So flying here from high pressure to low pressure. Well, now all of a sudden, the pressure starts to get a little bit lower. So here's what happens, is that all of a sudden now, he's going to see a reading on his airplane that says he's a little higher than he's supposed to be. And so what does he do? Well, the obedient pilot, he will go ahead and he'll reduce his altitude. Well, then he keeps flying and all of a sudden he notices he's a little bit high. Let's say he's 10,040 feet. He lowers his altitude. The pressure gets lower. Because remember what happens when the pressure gets lower? That thing expands, the numbers get bigger. But again, it's artificial because the pilot has not adjusted his altimeter setting for that lower pressure. And so he keeps doing this little series of step downs until all of a sudden he flies into instrument meteorologic conditions and hits something hard. That's the problem. So remember, high to low, look out below. Your actual altitude is going to be lower than indicated altitude. And that is the cause. It's not an instrument error, it's a pilot error. The pilot has forgotten or has just not changed the display in his altimeter to the new lower altimeter settings along his route. And you get those through the airports. Every single airport will publish a weather, and all of that weather will include, as you guys have heard, an altimeter setting. So you've got to stay on top of that. Now the opposite is also true, and this is where we get the phrase, low to high, clear the sky. And what that means is you're flying from an area of low pressure to an area of higher pressure without changing your altimeter setting. When that happens, your actual altitude is higher than your indicated altitude. Okay? Low to high, clear the sky. Your actual altitude is higher than your indicated altitude. Again, not an altimeter error. It is a pilot error in not changing the altimeter settings as often as you should. So that instance, you think, okay, well, gosh, in our part of the country, that's not a bad thing. Well, unless, of course, you show up at your airport that you want to land to and you're 1,000 feet higher than you're supposed to be. Now, all of a sudden, you've got this mad scramble. Okay, how do I lose altitude? Where do I lose altitude in order for me to get down to my traffic pattern altitude to land the airplane? And that can also be a problem. So again, the big thing, guys, is staying on top of those changes in pressures as you fly along, especially in our part of the world, and keep on top of those altimeter change settings. You can look here, find out what happens here when you have static vents blocked. Remember that you also have an internal alternate static source inside the airplane, so that in the unlikely event that your pitot tube and your static vents all become blocked, you can open those lines up at least inside the cockpit, and that's going to help you. That'll help you more than. I'm still showing live here. I'm sorry, guys. I'm just looking down here at this thing, and I'm not sure why this is doing this, but I'm showing that we're live. I am praying that that's the case. Here, I hope we have not lost our thing here. Yeah, thing. That's pretty articulate here. Okay. I'm looking here, guys, and again, I'm looking at this thing, and I don't know why it's searching for devices on this network. There it is. It's still showing that it's live, so we're just going to pretend that it is. Yeah. So there's that. I don't have a good place to put that. Shoot. All right. Isn't this fun? So, in the unlikely event that the static lines, everything gets all blocked up, you still can open up those static lines inside. Now, that's not going to take care of your pitot, because your pitot tube, of course, that's outside, and you should have turned the pitot heat on prior to entering any visible moisture. And a visible moisture, of course, is called a cloud. Temperature errors. When we look at this, if you think, okay, pressure can cause us a different reading, you would think that temperature can. And where temperature really comes into play has to do with really, really cold weather. And that cold weather also is why we have a special advisory that we have for operations into airports where the temperatures are really cold. When we get to the instrument side of things, I will show you that and why that works. But understand kind of how all of that stuff plays out. Understand your altitude measures, okay, and know what indicated altitude is, pressure altitude, true altitude, absolute altitude, density altitude, and encoded altitude. Know what those are. Vertical speed indicator, as the name implies, it gives you an indication as to the rate of your vertical speed, whether you're going up or down. And it works similar to an altimeter, with one exception. The altimeter has a closed case in there with the static lines connected to the back. The vertical speed indicator has in the back of the case a teeny hole. It's a little bitty hole that creates what they refer to as this calibrated leak coming out the back. Because again, what you don't want, if you without that little hole, you'd have two altimeters, and while two altimeters may not be a bad thing, it's not going to give you a measure of your vertical speed, because remember, your vertical speed, it kind of creates that little hole in there, kind of creates this little delay that will show you then when you're climbing and by how much, or when you're descending and by how much. So that's what the vertical speed indicator does, along with that little calibrated leak. Now, one thing about this is that, let's say, for instance, all of your static lines become blocked. Let's say that your pitot heat is blocked, your pitot tube is blocked, and your alternate static doesn't work. You just wrench the handle off of it or something, who knows. What would you do? Okay, you can't open up anything, there you go. Here's what you do. You break the glass of your vertical speed indicator. That's what you do. Think about it. If now you don't have a sealed case, you're opening up this vertical speed indicator to your ambient pressure inside the cockpit. Your vertical speed indicator is not going to work, but what would you rather have? An altimeter or a vertical speed indicator? I'll take the altimeter, thank you very much. And the reason that you break the glass on that, again, is to open it up into the pressure inside the cockpit, and it is the least expensive of the pressure instruments to replace. So that's why you break that one. So in the event of emergency, break glass. Vertical speed only, please. Now then, gyroscopic instruments. Remember how that works. We had a wonderful presentation on gyroscopic instruments and kind of how these things work. And we have, again, this spinning disc inside this case called a gimbal that allows this thing to kind of spin, take advantage of this rigidity in space element. Most of the older ones are driven by vacuum pumps, which blow air over the vanes of the edges of that thing. A lot of them now are electrically driven. And the big thing has to do with failure of that thing to keep spinning. Once it's spinning, it's going to show a correct instrumentation. But if you have a power failure, if you have a vacuum pump failure, that thing will ultimately start to spin down or begin to slow down. When that happens, the indications on your gyroscopic instruments may be faulty. So that's kind of how that works. You can look there at your gyroscopic instruments. You'll see what that's all about. What is the alpha and the omega? Oh, that is correct. It is your attitude indicator. Understand what the attitude indicator does for you. Understand how it works. Heading indicator. That is another gyroscopic instrument. Understand how that works. Know that periodically, we used to have to every 5 to 15 minutes manually change the heading indicator because it wasn't an electrically driven instrument, and so you would have to slave it to your actual wet compass that you had up here on your glare shield somewhere. And normally they mount those away from your other instruments so that the electronic fields don't interfere and all of that. So that's kind of how that works. The new ones we don't have to do that with because they're electrical and they're also driven by the computers and they're also pull data from other sources. So that's how that works. Also know that whenever you have navigation information that is overlaid on top of your heading indicator, we call that an HSI, a horizontal situation indicator. HSI is going to be navigation on top of your heading. Okay? So there's that. And this, the inclinometer, turn coordinator, you know how that works. You look at this, know that all of that stuff works. The magnetic compass. This is the wet compass, or the old whiskey compass, as we talked about before. We use the magnetic flux, these lines, these isogonic lines that are around our atmosphere, which, by the way, the magnetic field around our Earth is why we have an atmosphere. And so we use, for right now, most all of the things that we do are based on true north, magnetic north, using our magnetic field here. And we also understand that there is a difference between true north and magnetic north. True north is going to be a geographic north. If you followed a line of longitude to its terminus at the top of the world, that's going to be geographic or true north. But magnetic north and true north are not geolocated. They are in separate places. North Pole, where Santa lives, that's going to be geographic or true north. Magnetic north is over some lake in northwestern Canada right now, moving toward Russia at about 32 miles a year. So it wanders around a bit. Some scientists say that perhaps within your lifetime, the North and South poles may switch. That's kind of one of those things that happens periodically, I'm told, in the Earth, as again that molten core in our Earth creating this magnetic field, and this thing moves around from time to time. So that's kind of the deal. But just know that true north and magnetic north are not in the same spot. So when we break down things with regard to navigation for our airplanes, we have to break it all down to magnetic north. And the reason that we use magnetic north in the wet compass is because everything else can fail. It is rare that your whiskey compass could actually fail. So navigationally, we break everything down to some form of a magnetic course, a magnetic heading, so that we know which way we need to point the airplane, and then we adjust for wind. So that's kind of how that thing works. Understand what isogonic lines are. If you look at this map, you will see that there are various isogonic lines that allow us conveniently to make adjustments to our calculations with regards to navigation. East is least, west is best. East is least, west is best. East, we subtract. West, we add. So when we see something here like 10 degrees east, what we would do to make that adjustment between magnetic and true is that we would subtract 10 degrees from our true calculations to get our magnetic calculations. On a westerly line of flux or isogonic line, we would add that to our calculation to true to get our magnetic. There is one line that kind of separates the east and westerly deflections on your isogonic lines. That is called an agonic line. The agonic line is the one spot where true and magnetic are going to be the same. Now, if you look at this, you'll see that when this book was published, that 0, or the agonic line, kind of went there just somewhere west of Tampa. That line right now is right here. It's just west of New Orleans. So it moves around a bunch. And you're thinking, wait a minute, aren't the lines on the runway painted on those runways to line up magnetically? Yep. So what do you have to do? You got to go buy a bucket of paint. Every once in a while, when these lines of magnetic flux are moving around, you have to change the numbers on the runways. I know. So that's what happens, is that periodically you have to change the numbers on the airplanes. Since I've started flying into New Orleans, they have changed the numbers on the runway. So that's kind of what you have to do when all of that happens. It's easier and cheaper to go buy a bucket of paint than it is to try to change the way that the world is sitting. So like this, even though in Aspen, where the world truly does revolve around you. So, know the difference between isogonic and agonic lines. So that is what we call with this, we would refer to this as magnetic variation. Magnetic variation. It is the difference between the position of the isogonic lines as it relates to true north. Magnetic variation. But we have something else called magnetic deviation. Magnetic deviation does not happen out there on the great big world. Magnetic deviation happens inside the cockpit. So think of the pilot as the deviant. Okay? Think of the pilot as the deviant. And in that, you have a card that will be somewhere either above or below your magnetic compass. It shows the deviation between the reading that you get on the compass and what is actual. The reason that you get some of these changes is because of the magnetic interference of the flight instruments themselves inside the cockpit, changing the way that your compass works inside that airplane. So for instance, if you look here at the deviation card, to fly north, you would steer 001. Remember, north is going to be 360 or 000. East, which would be 090, you would steer 089 to make that work. Most of these deviations, honestly, are only going to be a degree or two. What's a couple degrees among friends? Well, as a professional aviator, which is your mindset, you want to be precise. So this is the way that we do it, okay? Magnetic deviation gives you your deviation card or compass card, okay? Shows you a couple of things there, shows you how the compass is constructed, how it works. They occasionally have to spin that compass and these serviceability checks. We check those things. They can be bench tested. The avionics shops can do it. In fact, what they're doing to my airplane right now, because of the fact that I use cameras inside my airplane and I have one camera that's relatively close to that compass, they're actually having to spin the compass to give me another compass card because of the potential interference of that camera that's up there near that compass. So that's kind of why they do that. Also, we use that compass, remember, because we want to make sure that the compass lines up with the runway that we're on. So for instance, when you line up there on runway 18, remember we've lopped off the last digit, so that 18 stands for 180. 180 means that we're facing south. If we get some other indication on our compass, like here, for instance, in figure 10-43, if we look at that and we say, okay, this is it, we're kind of looking southwest here right now, well, that's not correct. And so we know something's wrong, and we need to get that compass looked at before we fly. Magnetic dip and compass errors, here's the thing here. So we have two different compass errors, and with those, we are going to have acronyms. So, acceleration errors. Acceleration errors, I want you to write down vertically, I want you to write ANDS. A-N-D-S. ANDS, that's the acronym, and write it vertically, A-N-D-S. ANDS stands for accelerate north, decelerate south. ANDS, accelerate north, decelerate south. Here's what happens. If you are flying on a general heading of either east or west, and you accelerate your airplane or you decelerate your airplane, that magnetic disc sitting in that pool, it dips and it moves around a little bit. When you accelerate, it will show a momentary turn to the north. When you decelerate, it will show a momentary turn to the south. So again, don't follow it. Don't change your heading based on your compass in those two things. When you are on an east or west heading and you are accelerating or decelerating. Accelerate north, decelerate south. Well, Mr. R, if that happens on an easterly or westerly heading, is there something that comes up if we're heading north or south? Excellent question, imaginary student. If you're flying north or south, there is another error that is possible. And we call this UNOS, U-N-O-S. U-N-O-S, write that vertically. Undershoot north, overshoot south. Undershoot north, overshoot south. Let me take you through these. The acceleration errors, they talk about this right here. There's the ands, okay? Here's the turning error. The turning error has to do with this. The turning error is the fact that when you're going north, that's when that compass wants to run home to mama, okay? That's when that needle is sitting north. Well, you start to make a turn away from north, and the compass kind of wants to stay there. It kind of wants to stay at that northerly indication. And so it will lag behind your turn. When you're heading south, and I don't want it to look like south, you know, like I'm making some form of you know, proclamation about heading south down, you know, that's necessarily a bad thing, okay, just so you know. So when you're heading south, what happens is as you turn either left or right from that heading of south, that compass will actually lead your turn going either direction, coming in a southerly heading. Overshoot north, undershoot south, okay? Undershoot north, overshoot south. Undershoot north, did I say that right? God, I don't know. Stand by. Oh yeah, oh yeah, okay. So when we do that, turning from that southerly heading, it's going to want, the compass is going to want to go faster than you're turning for just a little bit. It's not going to be anything crazy, but it's going to be a little bit. Here's where this comes into play. When you are learning your instruments, you are going to learn how to make standard rate turns. Standard rate turns mean that you're turning that airplane 3 degrees per second. That means that in 2 minutes, you will turn that airplane in a 360 degree circle, okay? So if you think about going 360 degrees in 2 minutes, you'll go 180 degrees in 1 minute, you'll go 90 degrees in 30 seconds. In 15 seconds, you'll go 45 degrees. Do you kind of see where I'm going here? Why is this important? Because let's say that all of those instruments fail and you are told you need to turn to a different particular heading. You can time that turn so that you know exactly how many seconds it should be before you get to that particular heading. And it's one of the maneuvers that you're going to learn to be able to perform. So knowing that, this is kind of one of the things that we have to keep in mind when we're on that southerly or northerly heading or accelerating or decelerating the aircraft. Okay? So we have to know that stuff. There's that. Glass cockpit. We've talked about this there before. You understand the nature of these things. The difference is going to be is kind of how they operate. We use air data computers. We use accelerometers instead of some of these other instruments, these electronic, what we call MEMS, micro electrical magnetic systems. Mechanical systems, micro electrical mechanical systems that operate in much the same way as like those little hairs operate inside your vestibular tubes, inside your inner ear, you know, for positioning, etc. So you can look here also AEROs, automatic heading and reference systems. You have laser ring gyros now. We don't really have those much in our airplanes here, but we do use lasers in these. We use a magnetometer as opposed to like the magnetic fields, and that's kind of it. I don't know, you'll look in Big Blue and see what questions that there are with regard to instruments, but that's it. Guys, if you know those things right there, you will be ready for this quiz tomorrow. Yes, I said quiz tomorrow. Quiz tomorrow on instruments, okay? So that's going to be the quiz. After we're done with that quiz, time permitting, we are going to get the other presentations from the other groups that have not presented, and I want Kylie to present her presentation as well. So if we have time, and if not, we'll do that Wednesday morning. So tomorrow, Tuesday morning, quiz instruments. Okay, that's what it's going to be on. The old clock on the wall tells me here that I have gone for 40 minutes. And remember that we're recording 40-minute segments here now, give or take. And that's kind of what we're doing. We've got a couple of things that I'm going to be working on today because this thing didn't work quite the way I thought it was going to, but you know, what the heck. Anyway, there you go, guys. Hope everybody's doing great, and I look forward to seeing the results tomorrow on the old quiz on instruments. Where do you find the answers to the quiz on your instruments? Go to Big Blue, go to Prepware, pull up instruments, and just look. Those questions are going to be on the quiz tomorrow for instruments. Okay? Guys, have an awesome day. And with that, I'm going to hang up on you. Here we go. I'm going to do it right now. I'm going to press this little button. It's going to stop everything. Everything's just going to stop. Okay? There we go. I'm going to press this. Okay, guys. See you tomorrow.